Alice, Bob, Charlie and Eve all know each other. Alice is good friends with Bob, which I'll indicate by drawing an arrow from Alice to Bob. Having drawn all of the arrows indicating who is friends with whom, can you work out who the most popular person here is? Notice that everyone is friends with Alice, so it looks as though she's the most popular. We've managed to determine a specific property of Alice, her popularity, without inspecting Alice's personality at all. Don't worry, this is a video about category theory. We'll soon see that this way of defining properties, not by looking inside of an object, but rather by studying how it relates to other objects, is vital in our journey through category theory. Recall that a category is an abstract collection of objects and arrows that satisfy some requirements, which allow us to reason about a multitude of different areas of mathematics, computer science, and logic, all at once. But the price we pay for this level of abstraction is that we can no longer peek inside of our objects and assume they look like sets, types, or propositions, as doing so would mean that we can't generalize our results to categories with objects that look completely different. So how can we reason about specific objects in a category if we can't look inside of them? Well, just like how we found that Alice was the most popular person in a friend group without knowing anything about her personality, we can study objects in a category by considering their relationship to other objects via arrows. This method of thinking can feel unnatural at first, but this mindset is critical in the study of category theory. Let's get to grips with it by looking at an example. In the category set, our objects are sets, that is, collections of elements, and our arrows are functions. Let's look at the set containing a circle, a square, and a triangle, and the set containing the numbers 1, 2, and 3. These two sets have exactly the same number of elements, so in a way they're very similar. But how can we think categorically about this fact, and define this similarity without looking inside of these sets, but rather by looking at functions between them? The fact that these sets have the same number of elements can instead be interpreted as saying that there is a one-to-one correspondence between their elements. To make this rigorous, let's define a function f that maps a unique shape to a corresponding unique number. Since there is a one-to-one correspondence between shapes and numbers, we can define another function in the opposite direction that tells us which shape corresponds to that number. We call this function the inverse of f, written as f to the minus 1. Crucially, if we start at any shape and find its corresponding number using the function f, and then find which shape corresponds to this number using f inverse, we'll arrive at exactly the same shape that we started with. This is exactly the same as saying that f inverse composed with f is the function that does nothing to a shape, which is precisely the identity function on the set of shapes. This holds true the other way around too. F composed with f inverse gives the identity function on the set of numbers. So we've shown that two sets, A and B, have the same number of elements exactly when there exists a function f from A to B and a function f inverse from B to A, such that f inverse follows f is id on A, and f follows f inverse is id on B. That's a little more abstract than just counting elements, but we've now got an equivalent definition in terms of purely categorical concepts, which allows us to use this definition in any category. In fact, we call two objects in an arbitrary category that have this property isomorphic, and these special functions between them are called isomorphisms. We denote this relationship between the two objects by an equal sign with a little squiggle above it. We'll come across isomorphic objects quite a bit, as this concept beautifully encapsulates what it means for two objects to have the same internal structure without needing to peek inside of the objects to justify it. So with this new categorical mindset we've found, let's see what other interesting properties we can abstract. Considering that a set can have any number of elements, the sets which only have a singular element are rather special. We call them singleton sets. These singleton sets are just objects like every other set. So we'll need to characterize this property in terms of functions if we want to think about this definition in any category. With that in mind, let's take any old singleton set, say the set with a singular star in it. Let's now take any other object in our category. Let's call it A, which will contain any number of arbitrary elements denoted A1, A2, A3, etc. Let's think about a function f that goes from our set A to our singleton set. Starting with A1, f can map it onto, star? There isn't actually a choice of which element to map A1 onto, as there's only one element to choose from. F will also have to map A2 to star as well, and A3 to star, and similarly for every single element in our arbitrary set A. So there can't be any other function from A to our singleton set, as there's simply no room for choice. Any set with more elements will always have multiple ways of defining functions into it. So to sum up our findings, if we take any object in set, there must be a singular, unique arrow that goes from this object to our singleton set. Notice how this definition of a singleton set doesn't require us to look inside any of our objects, and as such, this definition is perfectly valid in any category. Indeed, an object in a category that has a unique arrow from every object in the category to that object is called a terminal object. So every singleton set is a terminal object in the category set. Remember that two sets are isomorphic when they have exactly the same number of elements. So this means that all singleton sets are isomorphic to each other in the category set, as they all contain one element. We can actually go a step further and prove that terminal objects are all isomorphic to each other in absolutely any category. To do this, take any two terminal objects A and B in an arbitrary category. There must be a unique arrow f from A to B, since B is terminal, and similarly, there must be a unique arrow g from B to A, since A is terminal. Finally, there must be a unique arrow from A to itself, and from B to itself, as there must be a unique incoming arrow from every object in the category to each terminal object, which includes arrows to itself. But recall that every object in a category must have an identity arrow, so our two unique looped arrows must be the identity arrows ID on A and ID on B. Then to complete the proof, we notice that G follows F is an arrow from A to A, which can only be the identity arrow on A, and the arrow F follows G is an arrow from B to B, so must be the identity arrow on B. This is precisely the requirement for these two arrows to be isomorphisms. So any two terminal objects in any category are isomorphic. This actually means that category theorists often refer to the terminal object of a category, rather than considering them each individually, as they are all indistinguishable from a categorical perspective. We'll denote the terminal object of a category by the number 1, which we'll see the reasoning for later on. To see some more concrete examples, the terminal object in our category of proofs is the true proposition, written as this special T, which is the proposition that is simply always true. This is quite easy to show. We just need to show that for any arbitrary proposition, we can give a unique deduction that the proposition true is indeed true, given that our arbitrary proposition is true. Well, Clearly we can prove that the proposition true is true from absolutely any assumption, and there is clearly only one such proof. So the proposition true satisfies the requirements to be the terminal object in the category of proofs. Lastly, in the category modelling a functional programming language, types with a single term will be terminal for the same reason as in set. We call this type the singleton type, and typically denote it as a pair of empty brackets, which perhaps confusingly is normally the name we give to the single term of this type too. This is all quite remarkable in my opinion. Category theory has allowed us to reformulate a definition in one area of mathematics and apply it in multiple others. This is a good time to mention that definitions like this that characterise some object up to an isomorphism are called universal constructions. The method that we use to define a universal construction goes as follows. First, we find the categorical version, which we call a construction, of the property we're after. So when defining the singleton set, we noticed that this construction would just be a single object in our category. However, we noticed that this construction isn't specific enough, as every set is an object in our category. So the second step is considering how every other such construction in the category uniquely relates to the actual construction we're after. Once we've found a unique property that the construction we're looking for must universally satisfy with every other such construction, we say that we've found a universal property. And that's it. A construction that satisfies a universal property is called a universal construction, and will always be unique up to isomorphism. Universal constructions can then be applied in other categories to hopefully expose some beautiful, oftentimes unexpected relationships between two seemingly different categories. Let's use this technique of universal construction again by trying to find a generalized categorical definition for the proposition A and B, which we call the conjunction of A and B. Recall that for any two propositions A and B in our category of proofs, there is a proposition A and B, which is true exactly when both of the propositions A and B are true. As an example, let A be the proposition Alice has black hair, and B be the proposition Bob is wearing a hat. The conjunction of these two propositions will be Alice has black hair and Bob is wearing a hat. Specifically, given that this conjunction is true, we can prove not only that Alice has black hair, but also that Bob is wearing a hat. Categorically, this will mean that there will be arrows from our conjunction to both of these propositions, as an arrow is a proof in this category. Let's call this first proof pi1 and the second proof pi2. This will be our construction then, an object with an arrow to two other objects. Is this construction enough to characterize this conjunction in our category? Not quite. There are plenty of other objects that we can also use to prove that both of these propositions are true, that we want to be filtered out by our definition, such as the proposition Alice has black hair and Bob is wearing a hat and Charlie is wearing sunglasses. Given that this proposition is true, we can use this to prove that Alice has black hair and that Bob is wearing a hat. Let's call these two proofs F1 and F2. Clearly, this proposition also proves that Charlie is wearing sunglasses. So it is definitely not the same proposition as the conjunction we're after. But we need to explain this difference in terms of purely categorical concepts if we want to define conjunction within any category. This is where step 2 of our universal construction method comes in handy. We're going to see how this unwanted proposition relates to the conjunction we want by thinking about proofs between them. Remember that our desired construction is true precisely when both of the propositions Alice has black hair and Bob is wearing a hat are true. So a proof that this conjunction is true is equivalent to a proof that Alice has black hair, along with a proof that Bob is wearing a hat. Notice that we have exactly these proofs from our unwanted proposition. F1 proves that Alice has black hair, and F2 proves that Bob is wearing a hat. So put together, they make a unique proof of our conjunction. We'll call this proof F. To explain this proof categorically, notice that using F to prove that Alice has black hair and Bob is wearing a hat, then using pi1 to prove that Alice has black hair, is exactly the same as our proof F1. This is also true for our proof that Bob is wearing a hat. First proving that the conjunction is true using F, then using pi2 to prove that Bob is wearing a hat, is exactly the same as our proof F2. So in categorical terms, we've found a unique proof F that when composed before pi1 gives us the proof F1, and when composed before pi2 gives us the proof F2. In terms of the diagram, we've essentially found a unique proof F such that the two paths from the top proposition to each of the bottom propositions are exactly the same. When every path through a diagram that start and end of the same object are equal, we say that the diagram commutes, and the diagram is called a commutative diagram. We'll see these sorts of diagrams a lot going forwards, as they graphically represent the very essence of category theory, composition. To finalise our universal construction, notice that this will be true for any arbitrary proposition X that can be used to prove that Alice has black hair and that Bob is wearing a hat. We can always use the two proofs F1 and F2 to construct a unique proof F that makes this diagram commute. This is therefore a universal property, and is indeed satisfied by our conjunction, so we've successfully found the universal construction of the conjunction of two propositions. Instead of calling this object the conjunction of two objects when we apply this universal construction in any arbitrary category, we call it the product of two objects, and write it as A cross B. We'll see why we use this term and notation another time, but for now, let's just reiterate the universal construction we have just found. We say that for any two objects A and B, there is an object called the product of A and B if it has arrows pi1 from A cross B to A, and pi2 from A cross B to B. And for any object X that has arrows F1 and F2 from X to A and B respectively, there is a unique arrow F from X to A cross B that makes this diagram commute. Saying that the diagram commutes is just saying that F1 will equal pi1 follows F, and F2 will equal pi2 follows F. As a final piece of terminology, we call the special arrows pi1 and pi2 projections. Let's put our understanding of this to the test by seeing if there are any types that fit this universal construction of a product in the category of a functional programming language. Let's take the two types string and integer, where a term of type string is some text like Bob or Alice. The product of string and integer, if it exists, would need to have a function pi1 to the type string and a function pi2 to the type integer. Let's think about what this product could be. We know that a term of type string cross integer would return a string when plugged into pi1 and would return an integer when plugged into pi2. Of course, pi1 could just always return a random string like apple, and that's still a perfectly good function, but it feels incredibly unnatural as a choice of projection. I would argue that, given that one term of type string cross integer can be turned into both a term of type string and a term of type integer, the most natural guess of a term of type string cross integer is a pair of a string and an integer. Let's call the type of a pair of a string and an integer string integer, with the term of this type being a pair with the first element being a term of type string and the second element being a term of type integer. For example, the term Alice21 would have type string integer, as would Bob24. Then since our projection pi1 takes a pair of a string and an integer and outputs a string, the most obvious candidate would be the function that just returns the first element of the pair. So pi1 applied to Alice21 would return Alice. And pi1 applied to Bob24 would return, you guessed it, Bob. Given that pi2 must take a pair of a string and an integer and output an integer, there's a just as natural definition for it. Pi2 would just take any pair of a string and an integer and output the second element. Then pi2 applied to Alice21 would return 21. And pi2 applied to Bob24 would return 24. So this pair type, along with these fairly natural projections, are a good candidate for the product of these two types. But to actually prove that this pair type is a valid product universal construction, we need to show that it satisfies our universal property. Let's give that a go. Consider any arbitrary type x, which has a function f1 of type x to string, and f2 of type x to integer. Then we need to show that there exists a unique function of type x to string integer that makes this diagram commute. The key observation here is that since f1 outputs a term of type string, and f2 outputs a term of type integer, together we can make a pair of a string and an integer by using f1 to make the first element and f2 to make the second element. Let's define the function f from x to string integer like so. F takes an arbitrary term x of type x, and then makes a string by plugging this term into our function f1, and makes an integer by plugging this term into the function f2. Then we simply put these two terms together into a pair, which we know will have the correct type string integer. This function definitely makes this diagram commute. We can check that by just chasing terms around the diagram and verifying that every path from the top to the bottom gives the same result. Let's check that. Any term x will be mapped to the pair f1 applied to x, f2 applied to x, under the function f. And then pi1 will return the first element, f1 applied to x, and pi2 will return the second element, f2 applied to x. Notice that this is exactly the same term that we would get if we went the other path through the diagram. Applying f1 to x obviously is the term f1 applied to x. And f2 applied to x is clearly the term f2 applied to x. Since this function f is also completely determined by the two functions f1 and f2, it is completely unique. So there we go. We've used universal construction to show that the product of the two objects string and integer in the category induced from a functional programming language is the pair type string integer. In general, for any two types A and B, the product A cross B is the pair type AB, with our two projections being the functions that return the first and second element of a pair. Of course, since the product is a universal construction, any types that are isomorphic to this product type are also viable products. To really put your understanding to the test, why not show that the type BA is isomorphic to the type AB by finding an invertible function between them? Then verify that the type BA also satisfies our universal construction, so is a valid product of the types A and B. So to summarise what we've learnt this lecture, we've found a way to abstract definitions of interesting objects by using universal construction, like singleton sets, or the conjunction of two propositions, which has allowed us to apply these definitions within any category. We've seen that exactly the same definition gives the singleton type and the true proposition, and precisely the same definition gives both the conjunction of two propositions and the pair of two types. Perhaps these are both strange coincidences, or maybe there's a more profound relationship between the category of proofs and the category induced from a functional programming language at play here. Don't worry, we'll come back to this question another time. I would encourage you to apply what we've learnt today to the category of the ordering of integers that we saw right back in the preliminary lecture. As a quick reminder, our objects are integers, and there is a single arrow from one integer to another if and only if the first integer is less than or equal to the second. First, verify that this is indeed a category, and then think about whether there are any terminal objects in this category. What would the product of two objects be, and can you prove it? Feel free to ask questions in the comments if you're stuck, and why not leave a like and a subscription whilst you're at it. Good luck, and I'll see you next time. Goodbye.